For over 12,000 years, we and millions of other species on the planet have benefited from an atmosphere which has given us a stable climate and life-giving air. But how often do we stop to think about our atmosphere and the air that we breathe? Hi, I'm Dr. Tara Shine, and I'm an environmental scientist. Welcome to the last of this year's Christmas lectures. We started by looking at the Earth with Chris, and then we explored the oceans with Helen. And today we're going to look at our own atmosphere, how it works, the effect we're having on it, and what we can do to protect it. This is Andy. Andy is Alice Hickson's safety diver. And as you can see, Alice is submerged under the water, and she's holding her breath. Alice has trained to do this for many years as a free diver, so please do not try this at home. As you can see, Alice has already been underwater for more than 1.5 minutes, holding her breath. I wish I could do what Alice is doing. I love the sea, I love swimming, and I get really frustrated when I'm not able to hold my breath long enough to chase that crab or that fish, and I'm forced back to the surface by the need to breathe. That's why I learned to scuba dive. And when I scuba dive, I use a tank like this one. Now, lots of people think this tank is filled with oxygen. They might even call it an oxygen tank. But pure oxygen at depth would be toxic to my body. Instead, this tank is filled with compressed air. But what is in the air that we breathe? Perhaps because we can't see it, that's why we take it for granted. But what if I cooled this air down? And by that I mean, what if I cooled it down a lot? To minus 200 degrees Celsius. At that temperature, the gas becomes liquid and we can see it. So what I'm going to do is pour this into this container. As you can see, it's a clear liquid. This is nitrogen, liquid nitrogen. And nitrogen makes up 78% of our atmosphere. I'm filling that almost up to the top. It's bubbling all over the place. So there's not just nitrogen in the atmosphere. What might be in this red flask? Let's pour that out. It's a beautiful blue color. This is oxygen, liquid oxygen, that life-giving gas. 21% of our atmosphere is made up of oxygen. So that leaves 1%. And 1% is made up of trace gases like argon, methane, and this here, 0.04% of our atmosphere is made up of carbon dioxide. And it is this same gas, carbon dioxide, that's building up in Alice's body right now and making her want to breathe. So let's go check on Alice. Wow, look, Alice has already been underwater for 3 minutes, 50 seconds. As I've told you, she is trained to do this. Alice is the UK World Champion Women Free Diver. But let's get her up now to talk to her about what she's doing and how she does it. Andy, can you give her a tap for me? So she's at 4 minutes and 10 seconds. Amazing. Alice, 4 minutes and 10 seconds. I don't know how you do it. I wish I could do it. That's incredible. How do you feel?
I'm all right.
You're all right. You're just no bother.
Yeah.
Tell me, how do you do it? How do you resist the urge to breathe?
Stubbornness.
Stubbornness.
And lots of practice and training your body to get used to the tolerance of the build-up of carbon dioxide and lactic acid and lots of practice.
Do you also need to be very relaxed?
Yeah, it's as much a psychological thing as it is a physical thing.
What kind of records do you hold?
All the British pool records and then the depth records. So for no fins, which is swimming as deep as you can without fins, a bit like breaststroke. Mm-hmm. So I can swim 60 metres deep under the water and back without fins. And then can hold my breath for 6:58 is the official record.
Wow.
Yeah.
And you didn't do a whole lot of like kind of stuff before you went down.
Hyperventilating makes it dangerous. That's not a good thing. It's more about being relaxed.
Thank you, Alice. That was just amazing. I can't believe you stayed under for 4 minutes. Thank you.
Thank you.
Carbon dioxide is a waste product from the production of energy in our bodies and from respiration. So we breathe in oxygen and we use that along with glucose from our food to produce energy. And the waste products from that process are water and carbon dioxide. Hello and welcome to our virtual audience. Lovely to see you. So if I use a camera like this special camera here, I can actually see the CO2 being breathed out by Malcolm. So if you have a look here on the monitor, you can see the CO2 being breathed out. And luckily, what is a waste gas to us is fuel for plants in photosynthesis, where they use this carbon dioxide to create oxygen. So thank you, Malcolm. But how could something as natural as carbon dioxide, something we breathe out, be bad for us and cause pollution? Well, when we burn ancient carbon stored as fossil fuels, we emit carbon dioxide. Now, fossil fuels were formed millions of years ago. They were formed when plants and other organisms were laid down in decomposing layers under sediment and rock. And when we burn that fossil carbon, it emits much greater amounts of carbon dioxide than Malcolm did when he was just breathing. So what we're going to do here is a little experiment. Very exciting. So we are going to together, Fran and I, we're going to set some coal dust, some fossil fuel alight. And we're going to see what kind of energy we can get from that and how much CO2 can we produce from that. So audience, we're going to need a countdown for this. With me, 5, 4, 3, 2, 1. Look at that. Imagine if we can get all of that energy and that huge amount of carbon dioxide from just a few little grams of coal dust. Imagine that on the scale of a power station or on the scale of thousands of power stations. That is the energy we have been using to develop our countries, to industrialize for over 200 years since the Industrial Revolution. And the result of that is that we have put an awful lot of carbon dioxide up into our atmosphere, enough carbon dioxide to profoundly change it. So if we look up here at our globe, we can see these concentrations of carbon dioxide swirling around our planet. All that yellow and red is showing us these higher concentrations of carbon dioxide in our atmosphere. So back in 1850, there was 286 parts per million of carbon dioxide in our atmosphere. And now today we have increased that to 415 parts per million. So carbon dioxide, one of the greenhouse gases, along with other greenhouse gases like methane, is causing our planet to warm. And we have already warmed our planet by between 1.1 and 1.2 degrees of warming. So our planet is now a degree warmer than it was when we started the Industrial Revolution. So 1 degree of warming might not sound like a lot. Is it really a big deal? Well, let's think about it in terms of our own bodies, okay? So you're all getting your temperature taken all the time at the moment, yeah? To get into the dentist, sometimes into a shop or a restaurant, you might have to have your temperature taken. So our average temperature as human beings, what it should be, is between 36 and 36.8 degrees. So this is what our normal temperature should be. And if that increases by 1 degree, okay, because we've been talking about 1 degree, to 37 to 37.8 degrees, well, we're still okay. We might feel a little bit hot, a bit flushed, but we're not unwell. But if we look at the upper end of this temperature here, and we increase our temperature by just 0.2 degrees Celsius more, up to 38 degrees, we're now suddenly in the threshold of being unwell. We'll have a temperature. We might even have a fever. And so every degree and every part of a degree of warming matters to our health, but it also matters to the health of our planet. What's also important when we think about how the Earth is warming and how unwell it may be getting is that that heat rise, that increase in temperature, is not evenly spread across the globe. So how you feel this warming depends on where you live. So if we look up here at our chart, we'll see that the warming is most intense in the Arctic. We can see areas of warming over our oceans as the oceans absorb the extra heat. And we can see warming over the continents, over the big land masses. And if we go over here to our globe, another continent that's warming a lot is Africa. And here over the Sahel and the Sahara deserts, places that are already really hot, it's getting even hotter. And in a country here called Chad, temperatures are rising faster than the global average and rainfall is decreasing. But don't take my word for it. Please come over with me now and we're going to talk to Hindu Umaru Ibrahim, who is an indigenous woman from Chad. Hello, Hindu. Good to see you.
Hi, Tara. Good to see you too.
How are you keeping?
Oh,
I don't
hot.
need to ask you that. Hot. So, Hindu, can you tell me how the climate is already changing in Chad?
We already have plus 1.5 degree. And that's mean for us, the Lake Chad, who is the bigger lake, who used to be in 1960, 25,000 kilometers squares, shrink to 90%. And imagine, communities are fighting to get access to the shrinking resources. They are leaving this place to become a refugee. So climate change is impacting the food security. It's impacting the livelihood of the communities, and it's creating the conflict among all the rest of the population.
And Hindu, tell me how you're using the 3D mapping to create this picture of how climate change is affecting your community.
Tara, this is the fantastic exercise of how we can use the science knowledge and traditional knowledge together. So 3D participatory mapping, it's gathering all the communities, those who didn't have the chance to go to school, but who know better than environment. They come, they put all them traditional knowledge in a scientific geographical map. And that can help to better see the areas who are the most vulnerable. The 3D mapping, it's a great exercise that can help the government to look at the communities and consider what they need to change the policies. And when we talk about climate change at the international level, so they need a local knowledge, and those local knowledge can be easily understood through the 3D participatory mapping.
Thank you, Hindu. That's fascinating about how we can blend traditional scientific monitoring and modelling with the indigenous knowledge that you're collecting in your community. So, Hindu, before you go, can you just tell me, does Chad produce a lot of greenhouse gas emissions?
Tara, no. In my community, there are no cars. We do not have big buildings. We don't have airplanes for ourselves. Even people do not have access to the electricity. So one person in Chad produces 0.06 of a metric of ton. So we are not responsible at all of climate change, but we are the most impacted.
Thank you very much, Hindu. So as we can see, a person in Chad produces less than 0.1 of a ton of carbon dioxide a year. So each one of these black balls represents 0.1 of a ton of carbon dioxide, what comes from one person in Chad. So let's compare this to some other countries in the world. Okay, first of all, we're going to go to India. So India is a developing country. It's industrializing fast. It has a very large population. And each person in India produces 1.9 tons of carbon dioxide a year. So more than Chad, 19 times more than Chad, but still very modest. What about if we look at ourselves at home in the United Kingdom? Each person in the United Kingdom produces 5.5 tons of carbon dioxide a year. So that's 55 times more than someone in Chad. So if we go over to the United States of America, each person there is responsible for producing 15.5 tons of CO2 every year, released right up into our atmosphere. So as you can see, that is so much more than one person in Hindu's community in Chad. And that's the thing about climate change. Climate change is very unfair. It's unfair in terms of who's responsible for causing the problem. But as we learned from Hindu, it's also unfair in terms of the impacts. So the people who are suffering the most from climate change are the people who are least responsible. This is called climate injustice. And if we look around the world, we can see that people are being impacted right around the planet in many different ways by climate change. On the globe at the moment, you can see wildfires spread right across the world. And while wildfires are a natural phenomenon, they're becoming more frequent and more intense now due to climate change. And if we look at Australia, Australia last summer experienced one of their most ferocious wildfire seasons. And in fact, research has shown that the weather that led to those wildfires was 30% more likely because of human-induced climate change. And in Europe, we're experiencing this changing weather in terms of gradual changes to our seasons. Our winters are getting warmer and wetter, but also in terms of more extremes like storms, floods, and heat waves. So as we've seen from Hindu, climate change is already having a very real impact on the life of people around the world. So let's play a game to see if we can better understand the impacts that global warming is going to have on our ability to feed an ever-growing global population. I want you to play with me. Wheel of Weather. Woo! So let's transform me into a game show host and let's play this amazing game. Okay, you guys in the audience, you all have cards. And on one side of the card, it's got blue for wetter. So if you think in any given year the weather is going to be wetter than average, you hold that up. Yep. And on the other side of your card, you've got drier with yellow sign. Yep. You're going to hold that up if you think in any particular year it's going to be drier than average. And what you can see on my wheel here is that I've got the same sign. So if it stops here, the wheel, this means it's a wetter than average year. If you held that card up, you get to keep it. But if you got it wrong, you must put it down. If you held up your yellow sign and it lands here, that means you can keep your card. Green means good growing conditions, and we all keep our cards. And the red is the danger zone, the current 1 degree of warming. The red means we get one of these extreme events, something like a flood or a drought, and we all lose a card. In the game, we're going to play 3 spins per round. And if you lose 2 cards in that round, then you must hold up your red out sign. So this represents 1 degree. Okay, audience, are you ready? You got your cards ready? Choose now. Okay, Ruben's gone for drier. Thomas for wetter. Millie's wetter. Ben is drier. Jay is wetter. Okay, we've got a good mix going on. Okay, let's spin the wheel and see who's going to get lucky or unlucky. Okay, so the really good chance of landing on green, but we'll be, yes! Okay, it's been a good year. Everybody keeps their card. Okay, this is a great start. Are we ready to go again? Choose now. Okay, cards up. Maxie's gone for drier. Could we be lucky twice in a row? We have been lucky twice in a row. Amazing. Everybody keeps their card. Okay, so this is the final spin in this round. You ready? Choose now. Okay, what to go for? Wetter, drier. Sunny days up there for Walter, very good. Who else has got a sunshine? Amelia's got a lovely sunshine. Great. Okay, Fran, we can spin the wheel. Any sense of where it might land? Ooh, so it's landed on wetter than average year. So everybody who guessed correctly that it was going to be a wetter than average year, well done. I can see Millie smiling, Maxie, Thomas, well done. Okay, but let's see how we fared overall for this round at 1 degree. Is anybody out, or are you all still in the game? Everybody's still in. Excellent, really good news. Okay, so this means although the weather is unpredictable at 1 degree of warming, most of us, in fact, in this case, all of you made it through the year okay and produced the food that you needed to be able to sell. So we're going to play the game again, but this time we're going to play at 3 degrees. Choose now. Okay, get those cards up. Time to decide. Ooh, lots of dryers over here. So this time, because we're at 3 degrees, we've upped the uncertainty and the unpredictability of the weather. So the chances of getting a wetter or drier than average year have increased. Oh, and it is a wetter than average year. Okay, so Florence, you chose correctly. So did Jacob. Jay and Max, well done. But that was only the first spin, so we can play again. Okay, are you ready? Choose now. Okay, get those cards up, get those cards up. Okay, a good mix of dryers and wetters again this time. Oh, wetter than average again. So Fern, you are lucky. You keep your card. Well done, you chose correctly. And we have a good few people that are out. They've lost both cards already. Woo! But we've still got some of you available for one more spin. Are you ready? Choose now. Okay, have you made your decisions? Let me look around the screens. Yes, everybody has made a decision. Okay, Fran, give it a spin. Oh, what's it going to be this time? Oh, drier than average. So, Ruben, good guess. Fern, good guess. Oh, we've got more out springing up all over the place. Oh no, Walter, you're out. Wow. So if I look around now at our audience, at all of your screens, I see that at 3 degrees, many of you were not able to make it through. You lost your harvest. And maybe your livelihood too. That's so sad. And this is the reality. If we allow warming to this amount, to 3 degrees, it gets really hard to make the right choices as a farmer. Thank you for playing the game. And whilst that was a really fun way to learn about the impacts of climate change, the underlying message is a really important one. At 2 degrees and more of warming, hundreds of millions of people are exposed to food insecurity, and farmers in the UK will struggle to make a living. The International Panel on Climate Change, the IPCC, which is made up of some of the leading climate scientists right around the world, tells us that in order to keep safe, we need to keep warming to below 1.5 degrees above pre-industrial levels. The difference between 1.5 and 2 degrees may not seem like a lot, just half a degree. But it's pretty significant. At 1.5 degrees, it's predicted that we will lose 70 to 90% of our coral reefs. But that rises to over 99% at 2 degrees of warming. And likewise, an extra half a degree of warming between 1.5 and 2 exposes hundreds of millions of people to hunger, to poverty, and to water insecurity. So what can we do to reduce greenhouse gas emissions and to stop our planet from warming anymore? Well, let's go have a look and see what's happening in our atmosphere. So this net represents our atmosphere. And as you can see, there's black balls of carbon dioxide falling into it. We've got this relentless stream of carbon dioxide coming into our atmosphere. And what we also have is a natural absorption and removal of carbon dioxide by the oceans and the land down here. These are the balls that I'm taking out. This is the natural storage by our planet. But as you can see, there's way more going in than are coming out. And what we need to do to hold global warming to safe levels is we have to balance the amount of carbon dioxide that's going in with the amount of carbon dioxide that we're taking out. And the first thing we need to do that is to reduce our emissions. So what we're going to do is look at how to do that. And we're going to start in the electricity sector. So at the moment, because we still produce a lot of our electricity from fossil fuels, it's responsible for 25% of global greenhouse gas emissions. And if we look at what's going on in the UK at the moment, we can see where our electricity is coming from. So this is from yesterday, and yesterday 24% of our electricity was coming from renewable resources, from wind and from solar. But yesterday was not a very windy day, so the difference had to be made up with fossil fuels, a lot of gas, even some coal producing the energy that we need. But on average this year, the good news is that 37% of our electricity was coming from renewable resources. So we have the capacity to do a lot more. We really know a lot already about renewable energy and how to do it. And what we want to get closer to is what we had on one day this year, where we had 60% of our energy coming from renewable resources. So this is an area that's really exciting because we have the technology. We know what to do. We just need to produce a lot more renewable energy. And of course, the thing about renewable energy is we have to figure out how to store it. So we can use it on these days like yesterday when the wind isn't blowing and the sun wasn't very sunny. And what we want to do then is to either store that energy in a battery. So you all know about batteries, they can hold energy, but they lose their charge over time. So another way of storing energy is to convert excess renewable energy, say for example from this lovely wind turbine here, to convert that excess energy into a gas that we can store safely and store it even from this year to next year. So what we're going to do here is we're going to do an experiment, and we are going to turn electricity from our wind turbine into a gas that we can store. So we're going to do this through a process called electrolysis. So we're going to use the electricity coming from the wind turbine to perform this process where we're going to split water, H2O, into two gases, hydrogen and oxygen. Okay, they're going to flow out of this tube here where they're all making little bubbles in the soapy water. Okay, so we're going to just see if I can scoop some of these up so we can get a closer look at the gases. So I'm going to put on my ear defenders because we're going to do a little experiment with these, and I'm going to wet my hands. All right, I'm going to try and scoop up a big handful of these bubbles. Oh, I've got a good big handful. I'm very pleased with this. And let's see what happens. Okay, let's do a little countdown from 5, everybody. 5, 4, 3, 2, 1. Did you see that? Wow, all of that energy. Hydrogen is combining back with oxygen and giving us what we want, lots of energy. And the only byproduct is water. And because we made this oxygen from a renewable energy, it's completely pollution-free. But it is explosive. So to find out if there are safe ways for storing this fuel, please welcome Dr. Inas Abuhamid. Inas, you're very welcome.
Hello, Tara.
So tell me, why are you such a fan of hydrogen?
I'm a big fan of the hydrogen molecule. It's a really interesting molecule. First, it's the smallest molecule in the universe, and yet it has got the potential to solve the biggest problem that we have in the world, which is climate change. And why is that? Because hydrogen has got a lot of energy density in it. It's a leading candidate for that. So we can generate and store a lot of energy in hydrogen, and we would not need to produce emissions when we burn it or when we convert it electrochemically into electricity, because of the simple reason that it doesn't have any carbon to start with. So that's a very elegant solution.
It's fantastic. So it's a pollution-free energy source. So tell me, this is your machine. How is it storing hydrogen safely, and what are you doing with it?
So what we do here in terms of storing the hydrogen safely is that we simply don't store it as gas. What we do is we avoid that process, convert the hydrogen chemically into solid state. And I have here a bag. I have the material that we actually use in this reactor. It's a small amount of chemical powders that when we expose it to hydrogen, it absorbs a huge amount of it. For example, in this reactor, we can store 2,000 liters of hydrogen at a pressure that is equivalent to the coffee machine that we have in our kitchens.
So totally safe to have it here. And then this hydrogen is here, so whenever we want to, we can turn it back into electricity.
Exactly.
Can we do that right now?
Yes. So we have the hydrogen here stored in solid state. When we want electricity out of it, we will release it back to its free form, which is the molecule gas, convert that electrochemically using a fuel cell, which we have here.
Wow.
And that will basically give us power.
Excellent. So can we turn it on?
Yeah, let's turn it on.
Go for it. Ah! Just like that. It's so amazing. It doesn't make any noise, yet it is producing the energy already to turn on our hydrogen sign.
So it is safe, clean, and it doesn't have any noise.
It's amazing. I love it. So what else can we get this amazing device to power up? We have some things here in us that would be typical in any teenager's bedroom. So we can turn them all on with this amazing gas whenever we want to. But But Anas, is it just electricity, or what more can we do with
So
hydrogen?
this is just one example of all the electricity that we have in this small unit. We could basically use it to power our homes, or what's in our homes. Today we can't do it, but it's coming in the future because we're really interested to decarbonize our energy. But this isn't the only place where we can actually reduce our emissions without affecting our productivity. On the road, for example, the long distance that we could achieve with hydrogen, if we compare it, for example, to electric batteries, they cannot hold enough energy for as long. And hydrogen is a much better candidate at doing that if we wanted to have like a very long trip and not having to stop multiple times on the road to charge.
So the opportunities are so many with hydrogen, and I can see how certainly it's going to be part of a zero carbon future for us all. Anas, thank you so much for joining us.
Thank you very much, Tara, for having me. Thank you.
Although hydrogen is expensive to produce at the moment, it can help us to store energy, and we can turn it into electricity to fuel trains, trucks and buses. We can even use it to power planes. In fact, this year, the first ever passenger hydrogen electric plane flew right here in the United Kingdom. And I'm so excited for all of you to think that when you grow up, you'll be able to fly to see your family and friends without any pollution. So what else can we do to reduce the amount of carbon dioxide that we're putting into the atmosphere? Well, another really important sector is agriculture. So that involves food production and also land use change. And it's a little bit harder to reduce our emissions from agriculture and food production because we're not just talking about fossil fuels. We'll also have to look at other emissions that come from clearing land, from the livestock that we breed, from food waste, and even from the fertilizer that we put on the ground. So let's have a think and a look into the carbon footprint of our food. And to do that, please welcome, from the Great British Bake Off, Lottie Bedlow. Lottie, you're so welcome.
Thank you.
And you brought me some bread.
I have.
Did you bake this morning?
I baked this very lovingly myself for you this morning.
Look, it looks fantastic.
I love bread.
So, Lottie, have you ever thought about the carbon footprint of bread?
I can't say I have.
No, I don't think many people do.
No.
So, the carbon footprint of the average loaf of white bread, just like this, is 1,200 grams of CO2 equivalent. It's CO2 equivalent because there's methane and nitrous oxide and other things in there too, but we convert it all into CO2 to make it a little bit easier.
Okay.
But you may notice I have a lot of black balls here.
I have noticed.
We basically said the carbon footprint of that bread is the equivalent of these 100 black balls.
Okay.
And what I would love you to help me to do, because you're good at baking, is to help me reverse bake this bread. So we're going to go backwards through the life of this loaf of bread.
Okay.
Yeah?
It sounds confusing.
So you've worked hard to bake it, and now you have
you're
to
gonna undo
unbake it.
Okay.
Okay. So what was the last thing you did with the bread?
The last thing I did was to take it out of the oven.
So would you like to try out this lovely oven behind you?
I shall.
Okay. So while Lottie's putting it in the oven, obviously you have to turn an oven on to make bread. What temperature did you bake it at?
Well, the first 15 minutes at 200 degrees, and then the next 30 minutes at 170.
Okay. And how long was it in the oven?
That's maths. So that's 45 minutes.
45 minutes. Okay. So that's 45 minutes of an oven using electricity.
Yeah.
And electricity creates emissions.
Yeah.
And so baking the bread, that's using energy while it's in the oven for 45 minutes. Mm-hmm. So that accounts for 16% of the carbon footprint of the bread. So that's our first 16 balls in there. Okay. Lottie, do you like toast?
I love toast.
What do you put on yours?
I let it go cold, and I put a thick layer of butter, then Marmite, and you should see your teeth marks in it.
I just think that's all wrong. I like my toast hot, butter, marmalade. But anyway, it turns out that having toast is quite extravagant because freezing and toasting of bread, that accounts for another 25%.
Oh, okay.
Yeah, so obviously toasters use a lot of energy.
Yeah.
So there's another 25% gone in. It's filling up already. It's not even
really
baked.
is.
Okay, so let's work backwards from it was in the oven. Before you put it in the oven, the ingredients. What ingredients did you make it with?
So I used flour, water, and yeast.
Okay, so how much do you think about flour?
I think about flour quite a lot.
Yeah, do you have favourite kinds of flour?
So bread flour is what I'd use for bread, plain flour, self-raising, all different types.
And where do you buy it?
I buy it in my supermarket.
Yeah, perfect. Most people buy flour in the supermarket. So flour has to be milled. So we have created you a very magic reverse milling machine.
Fantastic.
Okay.
Thank you.
So how this works, because it's a bit tricky and fantastically messy, is you turn it upside down because it's reverse milling.
Yeah,
Okay, then you pour some of your flour from your ramekin in the top.
just some of it.
Just some of it, a good old dollop of it. And then you turn the handle and you see what magic happens.
Oh, it's
So
exciting.
turn the handle and woohoo! It turns back into grains of wheat.
Wheat.
Yeah, so fantastic. So that is the grains of wheat that flour comes from.
Okay.
So that process of milling, you're making a great mess.
Yeah.
No, just flip it over quick. It's okay.
Leave that
That
there.
process of milling, that uses energy. It happens in a big factory. That's another 3 balls gone in.
Okay.
Okay, tremendous. So we're back at wheat grains.
Yeah.
So wheat grains come from wheat. So a farmer had to grow the wheat in his field, and then we have to transport it to the factory to be milled, and then
Yeah.
we'll also have to transport it, I guess, from there to get to your supermarket where you bought it.
Yeah.
So that transport accounts for another 4 balls.
Yeah,
Okay. So we're definitely filling it up now.
we are.
Okay, but we're still not even halfway, really, when you think about it. So the wheat has to be grown. You haven't grown wheat in your garden?
Not recently, no.
No, me
Not
either.
a big wheat grower.
No, you're not a big wheat grower.
No.
Okay, so, but there are plenty of farmers in the UK that grow wheat. 80% of the flour in the UK is grown with UK wheat, so that's
Okay.
good. So we need some soil, I guess. Would
Yeah.
you give that a stir? So I guess a farmer would need soil, sunshine, rain, and then I think more than likely they will also use some of this, which is a fertilizer.
Fertilizer, yeah.
Okay, so would you mix a bit of that in with the soil?
Sure.
So fertilizer takes a lot of energy to make, so that's producing emissions. And then when we use the fertilizer, it also releases a greenhouse gas called nitrous oxide. And nitrous oxide is a really strong greenhouse gas. It's 300 times stronger than carbon dioxide. And what all of that means is that growing the raw materials for bread comes up to a whopping 41%
a
of its
lot.
carbon.
That's
That's
a
a
lot.
lot, isn't it? So I have to get this whole bucket and I have to not spill any. Okay. So that's all those 41 balls in. All right, I think we must be nearly there. How are you feeling about your loaf of bread?
I need to think more about baking my loaves of bread, but I feel like this is good. It's good to know where it comes from, and it's good to know the process it goes through.
Yeah, and the thing is, making anything has a carbon footprint.
Yeah.
So, but it's just understanding. It's really interesting to understand the different parts of it and where it comes from. Now, if you in the audience are any good at maths, you may have noticed that this does not add up to 100 yet. If anybody has been doing the arithmetic in your head. So there's 6 remaining balls in my caddy down here. Now, would you waste even a crumb of a loaf of bread that Lottie made you?
No.
No, I certainly not. I'm going to eat every scrap of it. But we do waste a lot of bread. Yeah, and that bread produces greenhouse gas emissions when it goes into a landfill. It releases methane. And actually, we waste 1/3 of the food in the world. It's
Wow.
absolutely desperate. And it produces 8% of global greenhouse gas emissions come from food waste. So the final 6 balls
Yeah.
come from food waste. So anything we can do, all of us, to reduce that waste would be good. So that's it, Lottie. I think we've come to the end of it. I am not going to put Marmite on the bread that you brought me.
Well, you're missing out.
I know. But thank you for joining us. Thank you for
having
helping
me.
me to reverse bake bread.
Thank you. You're welcome.
Can we have a round of applause for Lottie, everybody? We've just seen the significant amount of greenhouse gas emissions that go up into our atmosphere from food waste. So what can we do about it? Well, first thing is, I guess we should waste less food. And then for that unavoidable food waste, like the peelings and the scraps, we need to try and get those into a food waste bin where we can so they don't end up in landfill. Now, have you ever stopped to think about what happens to that food waste when it goes away in the bin? What happens to it? Where does it go? So it might go for industrial composting, where it's broken down in the presence of oxygen to produce a lovely fertile compost. Or it can go for a process called anaerobic digestion, where it's broken down in the absence of oxygen. and we sent our cameras to see how this process works.
So at the moment, we're standing in our reception hall. So the waste is collected from wherever it's created. That might be your home, it might be a supermarket, retail, hospitality, a pub, a restaurant. And it will be brought here and is then put into that big hopper in the corner. And there we've got what we call a hammer mill. So it's something with big hammers that will basically smash the food waste and separate the packaging from the food waste itself. So once the material has had the packaging removed, it goes through a series of shredders or macerators in order to make the particles very small. So from that point onwards, the food waste is always in a pipe or in a pump or in a tank. The first tank that it goes into is a little bit like your food cupboard at home, where you would store your food before it's being fed to the digester. And this is where the magic really happens. These are what we call digesters, and in these tanks are hundreds of different types of bacteria who all work together to break down the food waste into biogas. So the gas leaves the gas holder and goes through a series of these pipes, which then feeds into our engine. And in the engine, the methane part of the biogas is converted into heat in the form of hot water and electricity. So of the electricity that we produce, about 10% of it is used to run this site, and the remaining 90% is fed into the national grid. The digestate, which is the other end product, is a really valuable, what we call a biofertiliser. The fertiliser is picked up by local farmers who apply it to their land, and in doing that, they don't have to use bought-in fertiliser.
Please welcome Becky Greaves to tell us more about anaerobic digestion. Becky, lovely to see you. So Becky, we've learned quite a lot about methane as a greenhouse gas in the Christmas lectures this year and how potent it is when it gets up into our atmosphere. Can you tell us how you prevent methane from getting up into the atmosphere?
So we really carefully control the feed to our digesters to make sure that we produce the methane at the same rate that we can use it through our engines. And the tanks and the pipes that you saw on that video are all sealed. So there's no way that that methane can get up into the atmosphere.
What do you do with it then? You produce energy, electricity with it. How much electricity can you produce?
So on the video, you saw a large lorry reversing into our reception hall. Typically, a lorry of that size would hold about 25 tonnes of food waste. And once that's digested through our process, it would produce enough electricity to fuel an average household for over 2 years.
Wow, that's really impressive. And Becky, we saw at the end of the clip the biofertiliser that you're making. How can that help us to reduce the greenhouse gas emissions from agriculture?
So the farmer would have to apply some sort of fertiliser to the wheat in order to grow it. If we go back to your example of the growing the wheat for bread that you used earlier. And so by applying biofertiliser, we're giving that wheat those exact same nutrients, but actually we're not using those mineral or those synthetic fertilisers, which, as you say, produce greenhouse gases for their production. And to put it into context, that lorry that you saw, the digester or the digestate that was produced from that food waste would be enough to fertilise the wheat to produce 5,000 loaves of bread. What's really good about this process is that it's a closed loop. So actually, if you throw away a mouldy loaf of bread, we can turn it into biofertiliser and grow wheat to produce more bread. But more importantly, we also produce the electricity to bake that bread and for you to use it at home and turn it into toast.
Becky, that is amazing. It's just a whole lot of win-wins in the solution that you've told us about. Thank you so much for joining us.
Thank you for having me.
So we know what to do to reduce the emissions going into our atmosphere. We just need to stop burning fossil fuels and keep them in the ground. And we need to reduce the emissions from agriculture and food production. We just need to do more of it. But reducing emissions on their own isn't going to be enough. We're going to take a look again at our atmosphere. So what we've managed to do now by reducing emissions is to slow the flow of carbon dioxide into our atmosphere. But as you can see, it's still building up. We're still making the problem worse. So what we also need to do is remove carbon dioxide from the atmosphere. And our best ally in doing that is nature. As you remember, with Chris and Helen, we learnt about the natural ability of our oceans and the land to store carbon. And so if we protect nature, we protect ecosystems and restore them, we can remove CO2 from the atmosphere. And that is what we need to do to be able to achieve 1.5 degrees of warming. So nature is our best ally in this process. You probably know that trees have a great potential to store carbon and keep us safe. But have you ever thought about our soil? So soil holds 1,500 billion tons of carbon dioxide. So much. And within that, peatlands, which cover only 3% of the planet, they hold 1/3 of all that soil carbon. They're so amazing. But don't take my word for it. To learn more about peat and its wonderful ability to store carbon, please welcome Professor Andy Baird. Andy, thanks so much for joining us. Can you tell me what makes peatlands so amazing and why are they such amazing carbon stores?
Hi Tara, yes they are amazing. I mean, peatlands have been forming since the end of the last ice age, and over the thousands of years that have elapsed since then, they've been slowly accumulating carbon so that now we get to the present day and they are huge global carbon stores.
And Andy, can we use this cross-section of peat that you were kind enough to send me to explain this storage process, maybe starting from the bottom of the sample?
Yeah, of course. This sample was taken from a peat bog that is 6.5 meters deep. Now, we've only got a shallow bit of peat here, but even at a depth of 40 centimeters, this peat is old. So at that depth, at the bottom of the core, the plants that formed that peat, they were growing at the time that Shakespeare was writing his last play, so it's 400 years old. If we move up in the profile to about mid-profile, so about 20 centimeters below the surface, we're still below the water table there. And being below the water table means that decay of the peat is a lot slower. So this is part of the long-term carbon store that peatlands have. And then if we move up to the surface, we can see where all the dynamics happen. We can see sphagnum mosses. Now, sphagnum mosses, each year they sort of grow up vertically, and the lower part of the sphagnum, it dies and it gets added to the peat. It becomes part of the peatland. And if the amount of dead sphagnum moss being added to the peat is more than all the decay in the profile below, the peatland will get bigger and bigger. It will accumulate carbon.
Wow, so it's this whole process of keeping the peat wet that is helping us to ensure that it stores carbon.
Absolutely, yes. You need to keep peatlands wet. And that reminds me of two really interesting statistics. A 50 centimetre layer of peatlands, a little bit more than that core, a 50 centimetre layer per hectare holds more carbon than a hectare of tropical rainforest. Wow. And if we think about all the world's forests, they contain a lot of carbon, but peatlands contain twice as much carbon as all the world's forests put together.
They really are so amazing. But then, Andy, what happens if a peatland dries out?
If you drain a peatland, what you do is you lower the water table. And as the water table lowers, you allow air to get into the peat. And that means oxygen. And that speeds up the rate of decay, perhaps by 10 times, even more than 100 times. And decay produces carbon dioxide, and that goes into the atmosphere. So peatlands that are drained, they're big leakers of carbon dioxide into the atmosphere, if you like.
And Andy, why would we be draining peatlands? Why are we drying them out?
That's a good question. Well, drainage happens for a variety of reasons. Sometimes to grow trees for afforestation, so commercial forestry. Sometimes for agriculture. And also to make peat extraction more straightforward, easier. And people extract peat for a range of reasons, but one of the biggest reasons is to produce compost for your gardens.
Oh my goodness, it's so bonkers that we're digging up this amazing carbon store to use it in our gardens.
I agree. I think it's absolutely bonkers myself. And I think of it as being a little bit like dredging up all the coral in the Great Barrier Reef, crushing it and then sprinkling it on your garden to make it look more pretty. It's just madness. It's destroying a really important ecosystem. And I think peatlands are as important as our coral reefs.
So if they're that important, Andy, what should we be doing to protect them?
I think there's two things. The peatlands that are already in a natural condition, already wet, we need to keep them that way. We mustn't drain them, we mustn't damage them. And then the peatlands that are drained and currently leaking loads of carbon dioxide into the atmosphere, we've got to reverse that process. We need to block the drains, get them wetter, and they'll leak a lot less carbon dioxide into the atmosphere.
Andy, thank you so much for sharing all this information about peatlands with us. Everybody, Andy Bairds. So Andy told us that the most important things we can do for our peatlands is, first of all, to protect the ones that we have. But secondly, we need to re-wet those degraded peatlands so that they don't lose any more carbon dioxide. Okay? It's only by re-wetting them that they can continue to hold on to that carbon dioxide. But a bonus of this is that if we start to restore and rehabilitate our wetlands, then the vegetation will start to grow again over time. They'll be recolonized by things like sphagnum moss. And what that means is that our peatlands will, over time, over decades, between now and you becoming my age, they'll start to become stores of carbon dioxide again. They'll be removing it from the atmosphere and storing it safely in the peat. So peatlands are one of the most amazing ways that we can remove carbon from the atmosphere and store it safely. So let's go back and have a look at our atmosphere. So at the moment, we have slowed the flow of carbon dioxide into the atmosphere. We store more carbon by restoring peatlands and our natural ecosystems. There is still some carbon dioxide left in our atmosphere. And that means that the warming is going to continue, and we're going to have to learn how to adapt to climate change, how to cope with the impacts that it's going to bring. So we need to understand climate impacts, we need to plan for them, we need to prepare by building things like flood defences, but we also need to invest in people and make people better able to cope with climate change. Welcome to Taraville. Taraville is a small town on the coast of the UK that's vulnerable to flooding. And let me introduce you to two Taras that live there. Tara 1, which is this bucket. Tara 1 is our happy-go-lucky student. She comes from a well-to-do family. She's living in the halls of residence and having a great time at university, and she's in really good health. Tara 2, meanwhile, is our struggling student. She's living at home with her parents and her elderly granddad. She's holding down a part-time job to make ends meet, and she suffers from asthma, which is accentuated by the poor air quality where she lives. So one dark December night, Taraville is hit by a flood. Now the flood has hit. Immediately, both Taras are down in the red zone down here. They're both at risk from the flood. But let's rewind a little. So Tara 1 got a warning. Her mum, who is friends with the mayor and really well connected, gave her a call and said, Tara, I think it's going to flood. Nobody gave Tara 2 a warning. Tara 1 was able to prepare for the flood. She took all her belongings upstairs to her friend's room on the second floor and kept them safe. Tara 2 made no preparations. At the same time, she was tidying up after dinner, checking on her granddad and going to bed oblivious. Tara 1, when the flood hit, she was upstairs having a slumber party with her friend. She was starting to be really out of danger and in the green zone. Tara 2, meanwhile, when the flood hit, dirty flood water came through her house. Everybody rushed downstairs to try and get Grandad up the stairs to safety. All that rushing and the stress accentuated Tara's asthma, and it was just terrible. By 1 in the morning, Tara 1 is snoring. She's completely safe in her halls of residence. Meanwhile, Tara 2 and her family are being rescued in a boat and taken to an emergency shelter. The next morning, Tara 1 checks her room downstairs, see there's some minor damage, but she's got savings so she can replace things, and she had contents insurance on her belongings, so she's fine. Tara bounces back quickly. She's up in the green zone. She's no longer at risk. But Tara too, she can't even go home the next day. Her house is ruined. Her family don't have any savings in the bank, and they weren't able to get insurance on their house because they live in the flood zone. Tara too has to drop out of college to get another job. Grandad is in hospital with pneumonia, and it's several years before her family get back to normal. She continues to live at risk. So what can we do to make this sad story better? How can we make Tara too less vulnerable to these floods, to these impacts of climate change? Well, let's think about some things we could do. Number one, what if the town council in Taraville got their act together and built some flood defences? And what if they rehabilitated the wetlands so that they were able to create natural protection from flooding? What if they put in place an early warning system and Tara was able to get a text message on a phone telling her there was a flood coming? That would make Tara less vulnerable. And if Tara got that message in time, she would be able to prepare. She'd be able to get all of their belongings upstairs in their house. And she'd be able to arrange for Grandad to go and stay in a care home for the night so he'd be out of danger. And she would use her social connections to call a friend to come and pick her up and take her and her parents to safety for the night. In this way, when Tara would return to her house the next day, she would find that the damage had been limited, not too bad at all, and what was damaged would have been covered by the insurance that she was able to buy because she was eligible for insurance now that the flood defences had been built. As we take these steps to make Tara more resilient, she's less at risk. She comes up to being almost in the same category that Tara 1 was. And the point of this demonstration is that if we give everybody opportunity, it makes them more resilient to the impacts of climate change. And so as we've seen today, it's not just enough to reduce our emissions of greenhouse gases and carbon dioxide. We also have to take and remove carbon dioxide from the atmosphere and store it away safely, using nature as our ally. And we need to adapt to the impacts of climate change that we have already caused. But what I want you to know as young people listening here today is that we know what to do. We just need to do a lot more of it, and we need to do it with greater urgency. We have the solutions, we have the knowledge, we have nature and science on our side. But I am just one scientist, and we are all looking at the same thing, yet we see it differently.
I see that the energy we can access and the atoms we have are limited, but human creativity is infinite.
And I see that we're not separate to the planet, we're part of it. We're not just users of it.
And I see that we have a choice about how we live on it. Sometimes in the face of huge problems like climate change, it can feel like our personal actions are too small to make a difference.
But we can protect what we understand.
And we will protect what we care about.
It's up to us to take action and to use our voices. And every time we do, we create a ripple that keeps on growing. It starts here.